Hello everyone, in this video I will walk you through my homework for explanation code line by line, explaining the purpose of each variables and operating before running the code and descript its output in details. In the main method, I begin by using system.out.println to print the header homework for algorithm analyzes examples, along with separator lines to introduce the overall purpose and context of the program. Then I print a new line followed by one question, function time complexity, and call the time complexity example1 method. Inside in this method, I first print example function and then display I first print example function and then display the definition of a sample function that start with void example int n. Here I will illustrate two nested for loops. The outer loop for int e equals to 0, e smaller than n, e plus plus, runs n iterations, and for each iteration the inner loop for int j equals to 0, j smaller than n, j plus plus executes n time, print the sum of I and j, system.out.println I plus j. This demonstrates that a total of n multiplied by n, that is O n squared, operation are performed. Use explanation on its O n squared time complexity. Next, I print a new line followed by two questions, code fragments time complexity, and call the time complexity example2 method. In this section, I display a single for loop example for int e equals to 0, e smaller than n, e plus plus, to show O n time complexity. Then an example of nested loops for int e equals to 0, e smaller than n, e plus plus, for int j equals to 0, j smaller than n, j plus plus operation. To illustrate O n squared complexity and finally a logarithmic loop where a variable I starts at 1 and doubles each time for int e equals to 1, e smaller than n, e equals to e multiplied by 2 operation, demonstrating O log n complexity. After that, under the heading of a new line followed by these three question is power function to complexity. I define two integer variable with the statement int base equals to exponent equals 10. Here base represents the base of the exponential operation, while exponent represent the power. I then pass these variables to the power method using system.out.println base plus caret plus exponent plus equals plus power base and exponent. The power method recursively multiplies the base until the exponent is reduced to 0, returning on at the point introduce calculating, for example, 2 caret 10. Immediately following that, I call the optimized version power optimized, which applies a divide a conquer stretch powered optimized, which applies a divide and conquer straight by holding the exponent at each required step to compute the result in O log n time, printing the optimized result as optimized to caret 10 equals blah blah. Then under a new line followed by for question, Fibonacci time complexity, I define int n equals 10 and call the Fibonacci n method to compute the Fibonacci number using a classic recursive approach, which returns n when n is less than or equal to 1 and otherwise calculates Fibonacci n minus 1 plus Fibonacci n minus 2 including O to the power of n time complexity, printing the result as recursive Fibonacci Fibonacci 10 equals writes after then I call the Fibonacci dp n method where I create an array of size n plus 1, initialize its first two elements as 0 and 1, and then use a for loop from 2 to n to compute each subsequent Fibonacci number with fib I equals fib I minus 1 plus fib I minus 2. This approach achieve the result in odd n time using dynamic programming, printing dynamic programming Fibonacci 10 equals. Finally, under a new line followed by 5 question fast computer vs fast program algorithm, I call the fast vs slow comparison method where I set int n equals 1000 to define the problem size, then declare slow computer time unit as 1.0 millisecond per operation and fast computer time unit as 0.1 it's millisecond per operation. To simulate operation times on slow and fast computer respectively, I compute n multiplied by n computer and n multiplied by slower computer time unit for a fast algorithm, on on a slower computer, printing these results to compare their performance using an if-else block to determine which scenario is more efficient. Additional, I loop through to various problem size 10, 100, 1000, 10,000, 100,000 to calculate and display the runtimes, slow on fast and slow on slow in a tabular format, clearly indicating which algorithm performs faster at each size. In this way, I have thoroughly explained the role of each variable. this purpose of every operation and the intended function of each method. I then execute the code and provide a determined comment on these outputs, thus clarifying the time complexity and efficiency comparison between different algorithms.